Recording this session to reiterate what I've said before. I run two screens. The screen that you see is not the screen. The screen that you see, sorry, will be the screen that I'll be using for recording. Your feed, your comments, your inputs, your questions are actually on a second screen which is not recorded. So between it means that I can pick up any particular questions. If you have any burning questions as we're going through, and you do feel and you think, I want to ask that question but I'm not sure, send it me privately. Most of the time you'll find you're just a student who's asking that question, and a lot of others are just getting the courage up to do it. So if you feel like it's daft, it is not daft. Question is a question. What I tend to do is I tend to look at the question, I tend to read the question but not who sent it. So it's just because a lot of people do still prefer to be private. But again, I will be recording the screen. I have muted you all at the moment. As we're going through, can I please ask that you remain muted? If you do want to speak, you're more than welcome to speak, but can you just stick your hand up and then I can pause the actual recording, just because or else no, it's going to record the conversation as well, which would be very awkward. Again, but it will not, none of your personal details or any of your images are recorded on this side. So what I'm just going to do is share my screen. I always get this wrong. Is it this one? I'll just pull you over here. There we go. Right. So, what I'm going to do first is I do have a bit of a presentation that it's only a little bit of one. It's just to introduce exactly what we're doing. So let me just flip this over. So I'm just displaying, let's swap them slides. Right. So this is what we're looking at. This is known as the 4-bar linkage. It's quite a famous design, as I recently found out. If anybody knows about compliant mechanisms and heard of compliant mechanisms, this mechanism here was the original comparative between the compliant mechanism and this mechanism. The idea of the compliant mechanism is it's a material which has been designed to deform like an axis around one particular point. What it means is that you could have, in theory, you could remove one element of this assembly. In this case, it could be the lower arm here. This lower arm you could actually make hard and put some fillets into each side and then just allow it to deflect around that point. That's the idea of the compliant mechanism, but there's a lot more in it than just how I've described it. But what we're going to do with this is we're going to look at building this. So we're going to build this. Now we do have a criteria that we're operating to. We have a 2.5mm thickness of this particular component, and we also have 81 newtons applied to the end of the end location. So what I mean by this is where you're 313.885, it's hanging from this point. Now in this system so far, we've never actually applied multiple joints. We've never applied an offset, because don't forget it's got a 2.5mm thickness, and we've never really applied a weight hanging off the end of it. So this really takes what we've done to the next level. So what I did just to build it up is I solved everything by equation to find equilibrium of where everything sits. Now I have provided these in the notes. I've just realised. There we go. I have provided these in the notes, and what I've then done is collated these into a table of results. So within this table of results, what we're aiming to do is look for these calculated outputs and look to see if we're getting something similar to what's been provided by CD, for example. So in CD, you can see there, oh, you can't see there, that's very awkward. So let's look at BY and BX. Now we can test for BY and BX just to see what level of force is there, because we've got the joint. That will pull out forces for us. There's many different ways we can do it, but these are key things that we can look for. Right, so let's get to it. Let me just show you the notes first, because I do like to move on the notes, because it's something that you guys have got and it's something I've got, and if I stick to these notes particular, it means there's something for you to track along. Hence why I'm quite quite a stick in the mud as far as sticking with these notes. Again, as we're going through, if there's anything, any questions or anything, please stop me, and I'm more than happy to discuss anything. Let's have a look. So I'll go onto my module materials. Oh, before I forget, because I almost did forget, I did get some feedback. I don't know who's read this, because I'm starting to find nobody read the message I sent out. Horizon is now live. So under module information, you'll find Horizon install. Now, I'm giving you 3 ways to install it. I personally used the Horizon client. You can go by Adobe, or I just made a video. One of the 3. One of these 3 should support you. Now, to tell you what this is cloud-based computing. You will find ANSYS, Console, Inventor, SolidWorks, all on there. However, you will not find Matlab. What it turns out is Matlab's very, very meticulous about how they set up their licensing. But it does mean that the private install that I've sent to you all is legit. It's the right way of doing it. So what I did on there is under module materials, have I added this? I better have added this. Oh, that is awkward. Look at that. I've not even added it. Oh yeah, I have. Install Matlab, the bare min. Now, what I mean by that is what I'm particularly using. Just the bare minimum of what I'm using. Now, I think it comes back at around 3, it might be 4 gig that it uses. All of it together is, I think, 97 gig that it uses. But you don't need all of it, unless, I don't know, unless you're like a god.
Matt.
Hang on.
Dave.
Yeah, 2 seconds. Right, so we're back on resume recording, and let me just go back onto my module material, and under there I'll go on to notes, and on there you'll see I've got it down as tutorial 6. The reason I put on, right, so I've just had a question. I'm only reading this out just because there could be others as well. I can't check out Horizon install on recorded sessions. Please could you add me to the Blackboard? Now, if you are on that list, yes, I can just say that your colleague, because I'm trying not to diverge whoever's asking, but your colleague also messaged me last night as well. I was meant to do that this morning. Somebody cut me off because I was doing something else. So I can do that now, and then I'll add you onto this, and then you can see it. So, just to show you, bar linkage, the tutorial notes, and just because this session isn't about CAD, I've had feedback from people going, I don't know how to use CAD. That's fine, it's fine. This is not about CAD. I am not testing you on your CAD skills, testing you on your ability to understand the geometry and actually get a result from what you're trying to test against, making it as real as possible. So what I've actually done is produce the parts, because again, it's not about CAD. So when it comes down, it's down as a zip file. I don't know who's, I have had students before who've not been the most aware of zipping files. It's not a dig, that's just how it is. So 2 seconds, I'm just going to add, just for protection of said students, can you give me 2 seconds? I need to add these people on, so I'm going to pause the record. The question about has everybody been added to see, you all should now have been added. I've just added everybody on who has been requested. What I've done is download the tutorial notes. These are the particular set of tutorial notes. If you have been following me through both SolidWorks and Matlab, this is the original set of notes that I did. This was originally based purely on SolidWorks. I always provide sizes just because I want people to be aware of the sizes, but if you scroll down, keep going, what you'll find is solving this in Matlab. I need to really remove that because first generation has been removed now. This was a really old school way of doing it, and it was difficult but worth every penny. and into second generation. So this is the second generation one. I'm going to work my way through this right now, but I'd like you guys to be aware of what it is that we're doing and what we're aiming to actually get out of all this. So what I'm going to do is just minimize the notes. I've also downloaded my bar linkage. Now we need to tell Matlab that we're going to use a particular folder. So on my desktop I'm going to right click and then go new, and I'm just going to add bar linkage as a file tab. So under there I'm going to double click in, and this is now going to be my working folder. I need to keep this in mind. I'm just going to close off all my Internet Explorer just because I want to take you through the process of unzipping particular things. These are all my notes, so in 1 second, we got downloads. So I've got bar linkage there. Now I put it in a zip because there is an automatic unzip profile built into Windows. I do like to use 7-zip or zip. 7-zip is a high compressor, it's really good. So what I'll do is double click into it, and then what I've got is the connector, the crank, the frame and the rocker. And what I'm going to do is highlight them all. Do not think that you can double click that in and that's an accessible file, because that's you sitting inside of that compressed file. What we need to do is go into it and then drag across. I've left click, drag and drop, and all that'll do is take a copy of what's in that folder and make it an accessible folder. Right, so I don't know some of you this will feel a bit like sucking eggs because you'll have been told about this an awful lot. When it comes to addressing, the way that address process works is we're actually not making the geometry. We're using someone else's model, and then what we're doing is using their geometry in Matlab. And what Matlab will do is open that geometry. It will just open it, but it will not embed it. So what I mean is that models, STL files, step files will all be addressed to one particular location. Addressing works in one particular way. What it will say is it's on your C drive, it's on your documents, so it goes from C, then it goes to your documents or wherever it is, then it goes to a folder that in this case could be bar linkage, and then it goes to the file location. This is a quick overview of what an addressing process is. So it tells the system where to find it. Or you can have what's called an active path in Matlab. Now an easy way of doing that is if I bring my mouse over to where it says bar linkage, I'm going to right click. From that right click I'm going to go down to add to path, selected folders and any subfolders that I add. So if I click that, what you'll see now is that if you follow me, you'll see that your file has now become bold. It's no longer a grayed out. So it means that it's now added to the active file. So I'm going to double click in. Now you do need to do that every time. I'll show you why in just a second. Right, so that's just me setting up the locations. When we're going through this, I'm going to explain to you again about that addressing, because we're going to see that addressing emerge. First things first though, let's consider the scenario itself. So if I just bring this back and then just call onto here, we know, oh, I've just realised that does not explain very well. I suppose that one does. We've got a rotation occurring around the lower end here. So it's driven from this point. We know that these joints are not. These are just responsive joints to this rotation. And then we know that we have an 81 Newton force hanging from the end of it. If we say hanging, we can presume that it's 9.81 added, and what we're going to get is it will just be constant in this case will be Y, in the Y component set. So if it's continuous in the Y component set, what we're looking at is the strain on the motor. What we can do with this is phenomenal, because if we have a joint relation, if we have a coefficient of friction on each joint, and we wanted to look at what happens if it becomes worn down, what type of strain does it put on that motor, there is a way to predict if it's going to start offering problems as it's going through. So with that in mind, we need to first bring in Simulink. So again, your basic input. We're going to go with a blank. So I'm going to use a blank. I'm just going to actually pause my OneDrive. I don't know who finds this, but OneDrive really messes with my internet speeds. I think I'm just getting ripped off of my internet speed, to be honest.
Very, very well. At least next time I know I don't need to bring everything up. I'll just make sure that we don't have access.
Yeah, don't forget laptop. You need to make sure that's all set up as well.
Right, let me just come
Thank
back
you.
on. Right, I just had to mute you back up because it was obviously an accidental unmuting. Right, so back to the actual point. We're back on here. We know that we're going to have gravity acting downwards because we have a weight hanging off the end. We know that that is a particular point. We can choose to start this simulation from wherever we want. I always think it's best to start where all the action's occurring. And in this case, it's driven from this point. So that's where I'm going to start. Hence why I started that in the notes. So one of the first things that we always need to do is we need to set up the key active components. So in this case, it's the world. Wait a second. So I've just gone to library. I'm just going to minimize there, and I'm going to drop my Simscape, multibody, and these are the key points now that I'm going to be looking for. So I'm going to go utilities. From utilities, I need a solver configuration. Don't forget the solver configuration allows me to modify the inputs. I can choose relative tolerances from what I'm getting. I'm presuming that Matlab know what they're doing in this case, so I'm not really modifying it. I just want it to be there to allow that solver configuration if changes need to occur. I'm going to go utilities. I'm going to drag and drop a mechanism configuration. Finally, I need that all-important datum, the world datum, a starting point. This is where our 00 marker will be, our 0 point for the components. Again, I always call it a datum because there's quite a few will be CAD savvy. So I call it a datum in this case. We've got frames and transforms. I'm going to bring in a world frame. So this is now my world. Just sounds silly to say. And what I'm going to do is press Control, spin that round with a Control and R, and spin that round with a Control and R. Spin that across, and then bring that across. So, what's the first things? So let's just take a look back at the notes. So you're looking back at the notes.
Is this session recording, is it? Yeah, because normally you see a red border.
Yep, this session's recording.
Oh.
Yeah, it's recording. Oh, do you normally see that red border on that? Yeah, that's I didn't realise you guys saw the red border, but the red border is here.
Normally you see a little red button as well, you know, in the corner. It just says it's recording. Just let you know.
Ah, hang on. Yeah, you mean from other lectures?
Yeah.
Yeah, I don't use Stream. So, Microsoft Stream is an online method for recording, and if your internet signal goes a bit dodgy, it will record your screen going dodgy. So what I use is an on-screen mechanism, and it's called Expression, Microsoft Expression. And what Microsoft Expression does is it records the screen to my hard drive, and then I upload the file. So if my signal goes bad, the video will be extremely consistent. That's the only reason, that's the only reason why I do it. Right. So, what was I looking for? Oh yes, right. So if I just bring it back up, right there. So we've got a baseline. We have a frame. We have the crank. We have the rocker, and we have the connector. What I've always approached with this first is the actual fixed points. So I'm going to go with the frame. If I come down, come in, And what I'll do is, first things first, I'm going to go to body, because the thing is, the frame in this example does not move at all. So what I'm going to do is say file from solid, drag that over, I'm going to rename that and call that frame. Then I'm going to rotate it, bring that up into place, and bring that down. And then all I'll do is connect the frame in. Now we're going to add to this, but the thing is because the frame is fixed, there's nothing it does. So all I'll do is come in, and what the system does now is it says cannot make a visualization because there's nothing there. As ever, there isn't anything there. What we're going to do is we're going to come down, and I'm going to go to my folder and go frame, then click open. And if I press F5, and what I get now is my base frame component. Now with my frame component set, this is quite useful. So what we see here though, if I just expand this out, what you see there is an address. You see it's on my C drive from the user, and it just tracks to where it is. Now if I move this file somewhere else, the location will change. If it changes, this will crash. Now by using the live file, when I added the file at the beginning, what that means is I can use the active file. The only way I can do that is if I delete and just have frame.step. And what that will do is it means as long as I add that file location each time, it means it will always find it automatically. It's just a quicker way of being able to do it. It can be a little bit frustrating otherwise, because you can get caught up with all sorts and it's a pain in the backside. Right, now the density. What I need is a relative density, and this is far from what I need. So what I'm going to go with is, I think it's a steel, so 7700. Is it steel or aluminium? I always get myself mixed up on that. So I'm going to 7700. This is going to be the same material I'm going to use for the entire thing as I am going through. So this is my output points here, this is my mass, my center, my moments of inertia, and everything's been pre-calculated for me, which is great in this case. So then I'll F5 just to update, click apply, and then OK. Now at this point now, this frame will do nothing. Nothing will actually happen, because there's nothing there to make it happen. What I now want to do though is, I now want to bring in my next particular thing. This is where it just gets that little bit more tricky. So what I'm going to do is, if I go back to my frame, and then I'm going to go on to where we've got here. Under here I've got toggle frame location. Now this is where it's really important. If you zoom into your frame location, it tells you originally how this was drawn. So this was drawn from, well I should say I drew this from the datum on the circle and then extruded to give my 2.5mm offset. 2 seconds. That's fine. So I give it to the 2.5mm offset, and then I've given that distance across. So what that tells me is if I'm doing any particulars, I need to be aware of these sizes. So I'm just going to close that, and then I'm going to go into bringing in a rotation. Now this rotation is purely around, I'm calling up these notes as much as possible just to show you. If you look there, it rotates around this way. And what we need to make sure is that there's no collision. So what this will do is push things out. So first things first, let's just add these in and take a look. Right, so if I'm doing that rotation around, I'm going to go to joints, revolute. Now the revolute, as you'd imagine, is a revolving joint. That's all it is. So I'm just going to bring it up to here, and I'm going to add a revolute joint in. Now, I don't like to waste time with a lot of things. So what I'll do is right-click on here, 2 seconds. I'm just downloading the attendance list, that's all. Right, so now what I'll do is I'm going to add in my crank. Now the crank in this case is vital. Obviously it's my main driving point, it's the main point of revolution for it, and it's what the main thing is that's going to really drive this system running. So what I'll do is go to my frame. Again, I don't want to waste my time, I don't want to keep going backwards and forwards to get the same, so I'm going to right click, drag and drop. Now I know a lot will say, well, what's the point in doing that? What's that actually done? So if I click onto that now, I'm going to name that crank. Then if I come back across, double click, and what I'll do is I will change this now and go to, I can actually probably type this because it's in the list, so I'll go crank, then F5, and you'll see now that the crank arm itself is shorter. So what I'll do is put that up to there. So these two are now connected by a revolute. And what I want to do is just make sure that this thing's going to move. So I'm going to set a temporary speed and set it to 60 revs per second. So this is an initial moment, so it can be moving at that present rate. So what I'll do here, from my target state targets, from specific velocity target, from there I'm going to go priority, high desired priority, and I'm going to set this to revolutions per second, and I'm going to move this now to 60. Then this just sets this in there, and you'll find it matches with the notes as well. If you've not done already, hit save, so I'm going to go save as, and I'll call this bar linkage, or 4 bar link. Save that. Oh, God. Bloody Matlab with its names. I'll just call it bar link. There we go. So the reason I've done that is we're ready to just see this running. We're ready to start making small steps to be clear about exactly what it is that we're looking at. Oh, this is a great question. Great question. I just want to pause for this one. I just want to read the start of this as well. This might be a really daft question, but what is a step file from SolidWorks and why do we change it to step? Good question. So, SolidWorks has its own particular way of dealing with translation. And like a inventor file, now in the, I think this was in the 80s. In the 80s, a lot of people came along and went, right, we do a CAD system, we do a CAD system, we do a CAD system. And they went, right, we need a universal way that everybody can talk to each other. We're sick of it. What they did then is they, right, okay, then let's introduce IGIS, the international way of being able to communicate CAD across the files. What they then found is some CAD systems didn't take up the key aspects of this IGIS. So when you actually exported it, it didn't capture everything that you'd done. Then that then moved, and then somebody said, right, what we'll do is we'll put in step files. This will be a way of looking through that particular step of the process and looking at, can we capture things like key geometries, fillets, radii, things like that. Then in the 90s, somebody came back and went, nah, step's not working either, let's go back to IGIS. Then they went back to step and they said, right, we've got step working better. Now, at the minute, step is one of the best ways to translate CAD files through all different other areas. True, the thing of the matter is you cannot import direct outputs from a system. Now, if you're opening it and you're seeing a SolidWorks symbol, what SolidWorks is trying to do is go, use our software. It's the best. And that's genuinely all it is. So it's just a universal way of communicating the geometry that's already been produced. But it was a good question, and that's why I wanted to just give you some good detail in that. Right, so we've got that in there. If you've not done already, just hit run. Some key elements about this that I want you to be aware of. So this is just a crank revolving around that all-important frame. So all it's doing now is compiling. So I've hit run. And we go. You go, what? Oh. So ring that down. I'm going to run that again. So what you should find now is it's actually not doing much at all. What I'm going to do is shorten this time frame. Put it down to. I'll put it down to. Well, I'll actually put it down quite short. Actually, I'm just going to go something like 0.17. If I run it again. Because we're running so quickly, that's all it was doing. It's just because it was running so quick. The iterations, again, coming back to Excel, or the Matlab file that we wrote, that iteration process was so quick, it wasn't picking anything up. And all we're getting now is a rotation, and that's it. Which is great, however, when we spin this up, we've got mass level of penetration. There is collision throughout the entire thing. This is good, it's moving like we wanted to. It is bad, it's in the wrong position, and it's not running like we wanted it to. So, this session today, what I really wanted to focus on is the use of rigid transforms. We did a bit of it last week. Not much, I mean, it was just a bit, but we're going to use it quite aggressively today. And it's for that very reason. So what I'm going to do is, I'm going to leave that open for the minute because it's going to, well, I can close it when we're talking about. So what we know is that that all-important 2.5mm distance is not been set correctly. What I now need to do is I need to set it. Now, this is by using rigid transforms. Rigid transforms in this case can be set to variably. You can set.
Matt, just to stop you.
Yeah, go on, Dave.
You know when you're doing when you're actually putting your assembly together.
Yeah.
How come it didn't pick up that it was colliding with the other part?
Ah, yeah, good. This is a good question, really good question, because this really does not know. The thing of the matter is, so if I just open these back up. If we actually look at this, what you'll see is all it's actually referring to, let me just update that, it's only referring to the physics of the actual component. So it doesn't refer to the geometry.
It didn't identify two components, did it?
Well, it actually did, but it didn't identify them together. What you've actually got to do in this system is tell it that they're going to hit each other. Okay. So that is when you hit down the road of contact mechanics. But it's a phenomenally good question because in this case, these two are presumed not to be. What this system will do is say, right, I will do whatever you want me to, but if you miss out stuff, I'm still going to produce it and you'll just have done it wrong. And it's clearly that. There is further things to add to this. I do really want to look, well, I'm going to see if we can do this. I do want to look.
That would create problems further down the line, wouldn't it?
It depends which way you're looking at it. If you're considering the components hitting each other, continuously hitting each other,
you wouldn't have the natural thing of constraints, would you?
Oh yeah, of course you would. Your constraint in this case between them would be the relationship of the bolt or the relationship of the bearing where the joint is actually sitting. So this is where your coefficient of friction and your Reynolds equations and also Archer's law comes into play, or air resistance. So that's where they are really restricted around that. because in this case we're considering the system moving based on the material that we've got with the joints that are interfacing with it. So that's where our constraint really sits.
So if you'd have put that whole assembly together, the constraints, it would conform to the constraints, as in one part would move around and then the other part would move only a certain amount of the way. Do you understand what I'm on about?
No, what do you mean?
You've got your rocker arm that will only move backwards and forwards, haven't you?
Yeah, in this case, the issue that we have is that it's just wrong. The way I've done this, it's just wrong. And all I can actually do, let's say that this has been brought in as a job. All I can actually do in this case now is actually work around the geometry and look at how this has been put together and make sure it's a real representation of what's going on. Then once I've got that going on and it's actually running, I can look at incorporating Archer's law to give me how much material has been lost as wearing. Because Archer's laws, to do with the two equations as they're running together, to do with the two materials as they're interfacing, I can calculate how much has been lost. And it's a dynamic input as well. But as far as the interfacing goes with the two, then I've got to bring in further things. So I don't know if I've not got my toolbox on here. I have another toolbox I've been running, which is just contact mechanics. And I'm hoping in these sessions we're going to actually take a look at using contact mechanics. It's all right. It's all right to use. It's just a little bit intimidating sometimes. Right. So what I need to do is I need to move these two separately. So I'm going to go to my rigid transform. Bring in my rigid transform. Drag and drop it, and push that into play. Now, the way that this works is the base of where we were originally. The follower is the result of what we're telling it to do. So whatever comprises past this point will be operational. Whatever is former to this point is the former position where we were sitting. So I can rotate this joint. I can make the crank rotate in all different directions. I can translate the joint where I can say move in a particular area. So I can do standard axes, moving Z, moving X, moving Y. Now for this I'm just going to use Cartesian. Cartesian in this case is simply X, Y and Z. And I know that what's happened is it's not in the right position relative to Z. So all I'm going to do is I'm going to delete my Z. So I've just gone to the N0. I'm going to type in 2.54. because that's what's on the notes, and I've set my units to millimeters, click apply, and then OK. And if I run it again, what we now get is the criteria of what it needed to be. Let me just spin this around a little bit. So then if I run it, it's a little bit quick, so I'm just going to slow it down. So if I run it now, it spins round that particular point. And all I'm doing is operating to the assembly information that I have. So I've now got that set. I'll probably take this down by a factor of 10 as well. Actually, it's running. I only really need one rotation just to make sure that I'm operating. So I'll take that down by a factor of 10. I think that will give me just one. All I've done is take it to 0.017. Right, and ideally, now what I need to do is the exact same thing with the rocker. Now the rocker is the component to the front of it. The issue with this is again slightly different. The rocker now is at the end. So if I consider this, the rocker sits here, but I need to know what that distance is across from there. Now, again, I do like to just keep panning on these notes just so you can see. So the rocker is 152.4 between there and there. So if I come back down, I'm going to go to my rigid transform, going to bring in my rigid transform. Let's see who's asking. I'm going to bring in my rigid transform and I'm going to pan it over here. I'm just going to bring this up a little bit. I just want a little bit more space. and this is now going to be towards my rocker. Now the beauty is with this is I do know that my first Cartesian value needs to be that 2.54. It will need to be. But also I know that moving along that X component where the frame sits is that 203.2. Is it 200? I've got 203.2 in my notes. Why have I got that? Oh yes, because I was looking at the, yes, apologies, yeah. 203.2, not, because that's the rocker. Yeah, it's the frame I'm actually operating to. Get myself confused now. So what I now know is that in my rigid transform, I'm going to move this connecting point from on here, go my Cartesian, and I'm going to delete that and go 203.2. We're going 2.54, and I'm just going to delete that out and then apply. Click OK. Now this is the same time.
You're in meters, not millimeters.
Oh, thank God, thank you. That would have been very awkward. Yeah, you're right. That is monstrous. So I've gone millimeters. I have done it. I still do that to this day. Never get it right every time. So what I'm going to do is, now I'm going to copy these, but don't forget this has been actuated, so I need to remove that actuation. So I'm going to highlight that, bring that down, and I am just really being that lazy. Just, if I can, I will do. So spin that round, and I'm just going to call that rocker. Bring that into there, and I'm just going to remove that actuation. So this should just fall like a pendulum response, and it should be correct. It better be correct. So that's the actuation that I put on the crank. So I'm just going to drop that and click apply. Okay, and then run. Ah, I tell you what I didn't do. See the cranks there. I didn't actually add the rocker. So again, I'll come onto here. Because I'm operating from the active file, I can just type in rocker, click apply, F5. Some of you may want to do this. I like to do this to just give me a bit of definition, because I think this comes back to Dave's comment as well, which is a good comment of, you can't really see what, I can't really see it. I mean, some of you might be able to, not a problem, but I can't really see that clear definition between them. So all I normally do is go to graphics, and then I will genuinely just colour one in a different colour, and it really does help when visualising exactly what the hell is going on. So I'll probably go here as well. I'm probably just going to change that to a blue, and I know it seems a little bit over the top, but it is really useful. I'll probably keep that colour, to be honest, and stay with that red, just for these two sub points, and then the up connector, I'll probably change that to blue. But what it does is, if I run that, and then when we come back and we come to that, where's my component set now? So that's my X and Y. I'm just looking at the data, so I'm just trying to put it into something a bit more sensible. Right, there we go. So if I run that, slow it down a little bit. There's one thing that I've forgotten to do. I'm not trying to say I set it up, because I didn't totally forgot to do it. I don't know if anybody spotted it, but there is one thing I've forgotten to do. If I run that, this has perfect behaviour around the frictional joint. If that is the case, why is it not falling? And the truth of it is I've forgotten to put gravity in Y. So if I just quickly go to my mechanism configuration, drop out my 0 from my Z component, from my Y component, and swap them round, click apply, and now I'm should be in the gravity, and it should be moving them both. Let's just have a look. Slow that down a little bit. actually give me much at all. Let me just have a look at that joint. I'd be expecting a bit more activity from that joint. I'm going to bring in the next joint because I'm not sure about that one. Looked at that, thought it could have given me more connections between it. Right, what all I'm going to do now is start bringing in the other component sets. Now, if you remember what I was saying on here is, bring that note in, enter there, right. So what I now need to think about is there is a revolute around here and also a revolute here. So all I'm doing is building exactly as this has been made. Now the other thing about this is if you look at the frame, it goes an offset of 2.5 millimeters. Then it comes up to the connector, also offsets again by 2.5 millimeters. Again, all it's doing is just avoiding the collision. And all I'm doing is building around that collision. Well, I'm building as it's been designed. Right, so I'm going to drag and drop a rigid transform, drop it into place just in front of it. And I presume some of you have already figured this out, but don't worry, I'm going to work my way through it anyway, so I'm going to go translation. Based on the notes, based on the values that we've been given, I'm going to come back, go on to 101. I should point out there is actually an even quicker way of achieving this, but understanding frames and getting used to moving geometry around like this is a real benefit. So you are going to see both. This way is the particular long way of doing it, but I am going to introduce you to both. But this way, this really makes you get used to rigid transforms and getting used to. So the 101.61 is based on that all-important crank position, and all I'm doing is I'm putting a key point on there to where that sits. So that'll be relative to the crank. The minus 2.54 again is just that offset of material. So if I click on there, click OK, and I'm just going to drag another one over there like that. Again, I right clicked and dragged it over. A student showed me that. It's been such a benefit. It's crazy what a benefit that's been. I'm a huge fan of it. Right, so next what I'm going to do is bring that and copy that down, because again all I'm doing now is connecting, making sure that the rocker and the crank have their all important values in the right spot for me to operate with. And all I'm going to do here is I'm actually only going to push along, because I'm already sitting in that steady state. I'm only going to push along in the X component. I'll show you why in just a second. So if I come onto here and go translation, and from my X component, so I'm going to go standard axis, I'm going to go onto my X component, and I'm going to push that by 152.42, which again is that all important length between the rocker connecting point. Click apply, and then we're nearly at the final point to actually test this thing actually running. So if I now run it, I just want to make sure everything's moving as I want it to. Oh, that is not a good. Oh, this is because I've left front ports. What the system tends to do is go, you can't do that. You can't leave an F port there, because it's like leaving a circuit open on any type of ERE designs, anything like that. Leaving a circuit open is just daft. So that's what I've essentially done. Right, so I want to see and make sure everything is connected like I want it to be connected. So let's start with the crank. You see on there for the crank, you can see there that our connection points for this crank, we have rigid transform 2. I think it's transform 2, let me just have a look. So if I go rigid transform 2, you see our base connector comes here. We've got the following connector sits here, and let's just check. Oh, look at that. That might not work out well. We've moved in the wrong direction. Bummer, bummer. So you look on there, what I'm actually doing here is I'm bringing it home. This shouldn't be coming home, it should be moving on to the next plate. So this has gone in the wrong direction. Let me just check on my rocker. Is my rocker the same way? I suspect it is. So if I go rigid transform 3, go base, follower, base, follower, base, follower. So I could do with adding my 2.54 upwards. So what I'm going to do is quickly jump back in, because I need to make sure that these are in the right position. So if I come back, go to my transforms here. So I've got my negative. Just jump that out. Click apply. And if I come back onto here, because all I've done is just kept it open. This key here is update diagram. And if I go, because all I've done there is just edit my crank. So if I go back to my crank, so this was rigid transform 2, go rigid transform 2. Right, that's a little bit better. That is a little bit better. Now the reason I say that is our geometry. I'm presuming that the main connector was modelled like the rest. If it wasn't, then that's going to be problematic. We're going to have to fix it. But that's what I'm presuming. I'm just sticking with the same mentality of that I've done before, where it's connected these two together. I'm trying to connect the connector here, but we'll see how well this is going to work. And what I need these to do is to sit in line. So the what we call the follower needs to sit in line here, up to here. So that tells me that this side also really needs a Cartesian to go 2.54. So let's jump that in and go onto here, and let's bring that down and then take a look. So I'm going to go on my millimeters, I'm going to copy that out, and now I'm going to jump to my Cartesian. Place that in, drop that to there. So if I come back, let's update the frame. Alright, so now these followers sit in their same space. Now what's important with these is that they relate on the same point, because if anybody's wondering, this system is very much a stippler for if something does not line up. If the system does not line up and somebody's done it wrong, you're screwed. You need to make sure that everything runs in correct line. When they refer to a frame, think of it as a component line setting. You can't have multiple things bent all over the place and just make it work. Just for fun, I do actually have an example of where something's been done so badly that it didn't work right. So there was not fudge, but there needed to be a way to try and fix it. So I do have a great example of this. Right, so let's just jump back on. Let's come back out there. Right, now this is the big moment. This is now connecting the two together, which this is where there's lots of swearing that goes on. Well, there has been with me over the years anyway. So I'm going to right click, bring this across, and this, I can't, for the love of God, I don't remember what it's called, connector. So I'm going to go connector. Spin this round, and I'm just going to put my connector, well, it's the end part, almost the end part I should say, bring that connector to there, and before I forget, because I'll forget, I can't be bothered typing it, so I'm just going to put that in there like that, and then I'm going to delete out my address just to have connector, probably quicker just typing it. So I'm going to press F5, update that connector. So there's our key point for connection. Then what we're going to do is I'm going to just colour it. You can imagine in class last year we had some fascinating colours coming out of this. We had like pinks and God knows what. It turned into like a colouring in exercise. It's not really meant to be that, but whatever floats your boat. If I just double click in again, there was one extra thing I needed to see. I need to see that toggle, that all important, how has this been drawn? You see there? We have one connector already there. Nice. This is good news, because that means if we've already got that connector there, what we can do is we can presume that that is going to work right. So we're going to run this now and just see how it looks when it runs. Should be entertaining, believe me. So let's run it. Oh, what I'm just going to do is, if you do run into these, because I've left this open, I'm just going to highlight these. If you want to just temporarily turn them off, I've highlighted them, right click on it, comment out, and all it does is temporarily turns them off, just so we can test our present configuration. Right, so that's what we're getting. So let me bring that into something like that, and then let's slow that down. Let's just have a look. Perfect. I know it's not what you imagine, but it's a good start, because now what we need to do is just take a look around this assembly. Beauty is our components are not colliding. That was the all-important thing, that there was no collision going on. So that collision has been taken into consideration. I can offer more distance between it. So for example, if you wanted to take into consideration a particular O-ring. Now with nitrile, because nitrile is hyperelastic, when you have nitrile, its ability to respond to aggressive scenarios like this is fascinating. What it can actually do is, as you stress the nitrile will stiffen in some points depending on the composition of that nitrile. If you have a very strange behavior between it, you can model it into that behavior, and it will give you a true output of genuinely what's going on. Don't forget, we're not really considering the stress of the components, we're considering the work that's going on between it. And we're considering how well this thing actually runs when it runs. And we can also look at what happens if the components become rusted or damaged in some way. I say rusted a lot, it doesn't have to be rusted, it can be any type of operational damage it's suffered. So right, we've got that into place. Next thing we need to do is we need to now figure out how in the hell we actually get this connected to this. Because if I go like that, if anybody's, well, I presume a lot of you have really followed this, so if I, or not, if I run that, now because I've not given it a positional point here, if I click update, that's what it does. Now that's happened because there is nothing to tell the system where that's meant to be. And that's all that is. Just doesn't know where it's meant to be. You kind of look and go, okay, yeah. So we're going to have to take a little direction back. Let's take a look at the connector itself. So we've got 177.8. Okay, so if we go on 177.8 and then so if I bring that back, bring that across to there, there's a few ways we could do it. Obviously I'm going to stick with rigid transforms. The frustrating thing is when I show you the other tool, you're going to go, you've wasted my time. I've not wasted your time, don't worry. There's a few extra tools that I've not shown you, just because that will be cheating. Now I've brought in a rigid transform. So what I want to do is I want to move positive. I want to move positive from here to minus 177. Was it 177.87? Let me just have a quick look. 177.8. Okay. So what I'll do is bring that in. So I'm going to bring a transform, and I'm going to go standard axis, and what I'm going to attempt to do is move along that all important distance. So I'm going to go in the negative x in my millimeters, I do often make that mistake and put it in meters and go, where the hell's it gone? It's like 170 meters away. And if I go minus, now I'm doing that minus, well, you'll see in a second, I'm doing that minus because I'm trying to take into consideration where the components are meant to actually sit, where this joint's going to sit. So I'm going to go 177.8, and then click apply. Now let's just see how this looks. So I come back to my joint, bring this back across, and that's my present joint. So if I do update, so I've moved in the not the correct, I moved in the wrong direction. So let me just come back again. Ah, what a silly sod. I was already in the negative. So I've actually gone positive. So if I go like this, click apply, then bring it back, so you see there, that's why it's gone poof, straight over there. I'll click that. So we're now in a better position. Now what we need to do is the ultimate test of running it, because this might be a bit frickety at first. Happy days. So let's just slow that down. I just want to be sure I'm getting something realistic here. Slow that down. We can put more speed in it, we can do all sorts with it, but that's got it. Now, getting to that position is very tricky. We're now, as I say to everybody who's ever done simulation, please don't try and set up the most complicated simulation straight away, instantly, and just say, yeah, this is it. Does not work like that. Ever work like that. You set up the bog standard, the real massive assumptions, and you get the baseline running. Get that baseline set up, make sure it's running like you want it to, and then once you think, yeah, okay, this is running, then move to phase 2. Your phase 2 in this case will be, let's drop on more complications. Let's see what happens when this thing gets messed up. Let's see what happens to the motor. There's lots of things we need to know with this first. But what we're going to do is we're going to look at the torque that's coming out of it. We're going to look at the passive forces that's coming on that CD, which in this case is over here. But the thing is, at the moment, we've still not applied that all-important force. Now, that's not something that I've really shown you how to do yet. What we're going to do, though, is stick it on there because it's fascinating. So let's just drop that out and click apply. I think I've had a question. Let me just check. I like to just check that, so because for some reason everybody says Teams is amazing, but for some reason sometimes it just doesn't tell me everything that's going on. So right, we're now into that nice.
Hello.
Oh yeah, go on.
Can you go back to the actual model, please, if you don't mind?
So I'm just resuming on the recording. Oh God, I've had a comment from someone. Anyway, right. So I'm just resuming back on the recording, and let's snap that back in like that because I can at this case now. So the last thing that we've not done is we've not added the force onto it. What I think I'll do first though is start to pull out key value sets, key things that's going on about it. Let's pull out the torque that's occurring around the crank joints. So what I'd really like to know is that relation between here and here. So I want to know about CD. So I'm going to bring in CD, and then on from my CD, I'm going to do some sensing. Let me just think. Right, so what I'm going to do is bring onto here. I'm going to scroll that right down, and I'm going to go composite force and sensing. Then from there I'm going to go constraint torque. Now this is like we were talking about, Dave, about that constraint. Now this only refers to the relationship between them. Now the reason I put it on there because, let's face it, I'm going to mess it up. I'm going to do stuff to it to see what happens. Because all we're doing now is we're just playing around with how badly this thing can respond under different things. So I'll put on my constraint torque. Now you've got to remember at this point, it's very straightforward. It's going to be dead straightforward. There's not going to be much that comes out of it, because there's not anything that's really bothering it. But I want to set it up so that when I start to bother it, which I can't seem to get my words out right this morning, when I start to mess with it, it's still not doing any good. If I go to utilities, I'm going to go to my power stream to Simulink converter. And all I'm doing now is, don't forget, on Matlab it has the power stream. The power stream refers to a matrix of requirements, so the Cartesian values that are being recorded. So what I'm wanting to do is say, look, whatever you've got on these predefined values, drag them out, and I just want to see them. Now the total constraint is going to give me the total torque, it's going to give me the primary torque, and it's going to give me the secondary torque. So all I want to do is just pull out the first primary and secondary torques, and then I can start to mess with it. Now, if this does happen, and you've got a grouping of outputs, so in fact, let me show you. So I'll bring this in, and I'm going to go commonly used. I'm going to go scope and bring that out. Turn that around, bring it onto there. Now as this runs, this will be running unrestricted, totally unrestricted. So all I want to do is make sure that I'm getting something serious. So from here, because it's coming out as torque, as you can imagine, it's not going to be inherent, it's going to be Newton meter. And I'm going to run it. Oh my goodness. So if I run that round, this should be, I'm imagining I'm actually not going to get a lot from it, because again there's not a lot going on. So you can see here we've got our primary torque and we have our secondary torque. Now it can be a bit confusing as to what the hell is which. So what I tend to use is a way to dissect these into two separate components, so I can see them, because I look and go, is that primary, is that secondary, well, which way am I looking? So what I like to do is bring this across, and I use what's called a demu. And this here is my demu. And what this demu will do is take whatever signal's coming in and then divide it down. Now I know there is 3 coming in. On that output there was 3 there. So if I double click on there, I'm going to change that to 3. Bring this down just a tab like that. Push that into there. Right. Oh, I didn't want to do that. So what I'll do is I'm just going to now focus on just my primary and my secondary torques. I can add these together quite easily. So I'm going to put on 2. So I'll go 2. And I'm going to go tabs onto there. 2, apply. Onto there, bring that into there, and let's run it. So we can see from this that we spiked to the highest of, well, just under 6 Newton meters on a primary torque. And the secondary torque, this refers to the XY component, so if I add these together I'll get the overall torque of what's going on. But you can see here that it's a pretty much equal spread. I mean, on the secondary torque we end up with 7 Newton meters, but in the counter direction, just because of the component base that we're talking about. It doesn't really tell us much as an early doors. As an early doors, the first thing that I would start to worry about is that is a lot as a climb. Given the material that we're using, given the output that we've given it, it is quite a large climb. I mean, the momentum to actually drive this is not massive, but it is a heavy piece of kit. Because don't forget, we're running steel. The whole thing's made of steel. So you imagine that running that is quite a heavy bit of kit. I mean, it might be worth pulling out maximum torque from here as well, just to know the type of output that we'd need. But given that value, this could start to influence. I'm just pretending it's real, so it's not a real bit of kit. But this could start to influence my decision on how I'm going to actually purchase my motors. If anybody's worked with electric motors before, you'll know that you do not buy a motor to the maximum. So you normally operate about 25% above. So if I can get something that will give me 10 Newton meters of torque out on this, I'd start to feel a bit more confident that this will be supported. But it's not loaded at the moment. What we really need to do to get a true requirement of what, again, I know this is just a working example, but what we now really need to do is we need to put on that all important weighting. So how does it react when it's actually being dragged under? So we're not quite done with rigid transforms. I'm going to bring one last rigid transform in there. So I'm going to go rigid transform, drag that rigid transform in, and what I'm going to do now is go from the base of my connector, and let me just bridge up to here, and we're going, because it's equal across, we're going that all important 177. Oh, we know, that's a different, why is that not there? Oh, I've just realised that is not there. Should be equally spread. Well, let's just see if that's equally spread, because that should be equally spread. I've run these notes for years and I've only just noticed that. That is awkward. So it should be equally spread, and we're saying 177.8. And then what I'm going to do is, so I'm going to go standard value. I'm going to go, I think it's my positive X. And what I'm actually after here is just a point to add my loading to. So this isn't to do with the simulation as much. So if I just update, it's gonna have a panic because I've got an F statement on there. So my rigid transform 5, let's just see where that Cartesian sits. So rigid transform 5. Base, follower, base, follower. Base, follower. Base, follower. Follower, base. So this is now emerging because it's a separate. It's no longer connected to these. So what this actually means is I've got to take the overall thing into consideration. And just because I've already done this, which sounds really, here's one I made earlier, what we're actually going to do is we're going to put in the full length of this. So I'll hang this from one of the edges, just to give it a true representation of it's hanging from one of the actual joints. So I'm going to actually change this to a Cartesian, and as I said, I've already produced these values. It's just because I was aware of that these joints would be different. So I've got 3.2, this is the full length of the actual component set, 6.9, and then I'm just going to go minus 2.54. Whoops, 254, that's a bigger, not that one. So I'm going to go 2.54, remove the 0 out, and then apply. And then all I'll do is just come back to my joint again, and I'm just going to update my frame. Just make sure I'm moving in the right. There we go. Now, you see here, not the right spot. Damn it. I'm going to have to go back again. Tell you, I can't fasten my own shoelaces today. That then really should be sitting on the positive 2.54. And then let's come back and go update. There we go. And we've got that key point there. Right. Finally. I think. I'm kidding. Finally. We need to now add that force onto it. And then let's have a look at what's going on. Then I can start messing with the joints. Then I can start looking at damping around the joints. What happens if this joint has only this type of response? So let's then come back in and then let's go forces, and I'm just going to add an external force. This is the last stage, and then we have got that set up. So under my external forces, I'm going to come back, bring that back down, and I'm going to go force, and now I've got my key components here. Now this is a great bit of kit, is this one. I can just add external forces to something. You've got to be realistic. You can't just apply it to something that's totally flat. You've got to have, it's got to understand what it's doing. If it doesn't understand it, we'll just go, you're an idiot. That's good. That is not working. So what I'm going to do is say I'm going to put it in the Y, because if you remember, we've been operating that Y component. So I'm going Y. Click apply. Now by clicking apply, you'll see that it brings this in. Now this is purely because it's now saying you've defined that you're going to be putting things into Y, but what is the value that you're going to add? Now in this case, what I want to do is just bring in a Simulink to power stream converter. So this time what I'm doing is taking a single value and passing it in to that matrix, and because it's already been defined as Y, it knows to make that Cartesian Y component accessible. So it's great, it really is. So if I then go from Simulink to power stream converter, bring that over, tag that in, and then go commonly used blocks, because now I can just add my force. And what I'll do is go constant. Not quite done yet, but we're going to go constant. And I think it was 81 newtons. And then I'm going to come into this tab. First thing it says, you've got an input value. I'll give you a unit of 1. So this becomes dimensionless. Not what I'm after. I'm after Newton input, because that's what we said. From here it then says filter provider deliverables. How do you want to provide it? I'm actually going to say just keep everything constant. It's just this value I want. Don't give me anything sophisticated. Don't give me anything. Just keep it as a piecewise constant, which is just saying this is 81. Use that on this example. Then I click OK. And we should now be able to operate this as a component set. So let's run it again. Right, and that's talk about anticlimactic, and that's what we get. So what we know now is based on the follower, the force is hanging down and it's continuously active within it, and it's acting relative to gravity. And it's acting for that Y component set. So now, if we come back to torque, we notice that there's a few changes with it. Not much, but it's being dragged further, so the momentum drive for it, it is slower in its response. These spikes I don't like. See these spikes? That spike there would suggest that there isn't enough time for it to be properly calculated. If I look and see something like that, personally I will always come back out and then I'll go, right, what I need to do is just tidy that up to give me something realistic. So if I go model settings, and all I'm going to do is just add a little bit more time on this to solve. So it's on 3, and I normally just bump that up to 1 to the minus 5, just to give it that little bit more of an angle. And then if I run it again, we've still got these large spikes, but it is starting to change it ever so slightly. I probably would go back again and then just look at tightening up that tolerance even more to make it as smooth as humanly possible. Right, so based on our initial values that we're particularly getting, So initial calculation for MA was 3 Newton meters, roughly to the 3 Newton meters. So it is still needing some fine tuning, because MA in this case sits. I've actually not noted MA for this case. I don't realise how poorly that's actually been noted. And if I now try to look at my total torque, because I do want to see this total torque. So if I come back on, I'm going to add a third one onto here, and I'm actually going to add a third layout on that. There's something really useful here. So what I'll do is just tap sum. I'm going to go sum. This tool is literally as it sounds. So what I can do with this is just say sum this and sum this, and then feed that in. Oh, I don't like that. It's very messy. Feed that in. And if we run again, it's more like it. So we have our total out there. So you look between here and here, it is just beneath 3 Newton meters that it comes out at. So well, it's actually negative. So just to show you, so it is actually, it is still a little bit out, but it's much closer than what was particularly imagined. Now, because I've done that, and because it shows that I am on the right road to getting the correct value, now what I can do is mess with it. Now I'm in a position where I've verified that my values are somewhat close to what I needed them to be. But now what I can do with that is I can now move to the next phase of saying, right, what happens? What happens if? So let's just take a look at the actual assembly. So let's say, for argument's sake, something gets caught in the top here, and it restricts it, stops it from being able to move as nicely. Now something with a damping around a joint of something like 1 will be totally fused together and 100% broken down. Now the joint I'm referring to here actually is this joint, so that's what we're actually looking at. I can pull the full output out from here, but if I go onto here and say, right, what if this joint does become partly damaged? Now something like a journal bearing, you'd end up with 10 to the minus 9 Newton meters degrees in damping, so this will be something like 0.12245. Oh. Probably a couple more, but that would be starting to give us some type of off-the-shelf bearing. So if I run that and look at it, you see there, not much has changed. However, what if something gets caught in it? So what if that journal bearing is, its ability, it starts to seize up, it's not been lubricated? What type is that going to give? Right, so if I then run this, and then I come back again and run it, what we're starting to get is drastic. We're starting to get a build in these changes. But if I go quite daft and then just really presume that it's suffered quite a bit and then apply, what happens now is the motor's driving from here, it struggles to actually actuate it, and then we end up with, wow, there's not much really changing on that. Let me just ask them. Sorry, 1 second, just got a question. It's not a question referring to the direct. I'll need to message you outside of this. All I can say is that if you are brand new to the class, I have recorded all these sessions. All these sessions you will find on Blackboard. You do need to start taking a look and chasing up what's been going on in the classes for that reason. Now you'll notice here that it's not really changed as of much, so then it really prompts you to think, well, what if we look at the output of the actual joint itself? So if we go back to the composite joint, and we go, I can go total torque, but I like to go on constraint torque of just what's going on around it. So what I'll do is drop that out, and then I'll now take a look at this joint. So that's my output. If I come back out and I come back to here, and I'm going to just drop that to 0. And is there a big impact on the system running when it's like that? There's a slight change within these momentums for their outputs. A slight change. But what if the motor starts to struggle? Now, the reason I'm doing this is if I just go, okay, let's go daft, 0.1 on a damping coefficient, actually on the entire thing. If I run that, so that is what will be the motor exploding. I say exploding, failing. Now, if the motor gets to that point, what actually happens? Now, the reason I do this, what actually happens is the motor will seize. As it starts to seize, that power is still being provided to the actual motor. Due to some of the electronics on board, it's great, but that work needs to go somewhere. When that work does not go somewhere, what it will then do is start to heat up the coils. As the coils start to heat up, you will start to get large levels of temperatures burning. Some of you will have felt this in little tiny stepper motors. If you overload them, you'll find that they're red hot, they're burning hot. As it starts to happen, these will then burst into flames, and you'll get total failure, absolute total failure. Now, that's obviously a massive exaggeration as to what you get. Let's bring it down to something a little more or less. And when you actually look at something like that, which is not that crazy, but at these states now, yeah, it is quite. So if I make this a little bit more, so you see there, what actually starts to happen is its ability for the torque to put out drops drastically. As that ability is dropping, you can presume the ability to actually create the system to get into full momentum, that work has to go somewhere. So what you could do as a point of protocol is, if the system starts to drop its torque to a particular level, you can move to investigation. You can move to the next phase of that investigation. I mean, that's just me playing around with the torque output. I verified completely against what I've been doing. I've verified completely against what I've been doing, so it gives me a good solid position of that. If I go into employer, to the boss or whatever, I can actually go in and say, look, when I started this as a sim, I was clear about what I was actually getting, so I knew what I was actually producing, and now I can actually hang things, I can look at responses to it. Now, what I want you to do is save that. I'm going to save this anyway, and upload this to Teams. I'll zip it together, put it on Teams, and then you can download it and just take a look at what I'd put together. And I would, I shouldn't laugh, but I'm just going to show you one last thing, which may annoy a few of you, but it's important to do what we've just done. So we put on rigid transforms. We got used to putting on rigid transforms. I can click frames, and on here, if I click onto toggle, on here I can go, well, I want to add a frame, and if I click on that edge, I go, oh yeah, use that as a reference. Click select, and then save, and then what you see is it's a way to add a connecting point. So if I click apply and close, what you'll see now is I've got another point to add to. That's that can do away with the need for adding rigid transforms. However, you might not always have that as an option. Now, the reason I've shown you that is next week we are going to move on to building the Aprilia, and when we build the Aprilia, we'll be combining rigid transforms with just adding frames. And just adding frames is quick, simple, it's dead straightforward. I wanted to go through this the long way, so you're aware of how this is particular functioning. What I'll also do as well is I'm going to start releasing extra, not extracurricular, but extra notes that I have recorded before, just for your information. I've done a few on gearboxes, I've done a few on all different ones, and it will allow you to really start to stretch in the different areas that you know about. Because there is so much in this tool section that just this is the basic fundamentals of getting it working. Past here it gets huge, there's so much in depth, it's unbelievable. I'm going to stop recording now. Let me just click on my recorder, I'm going to stop that.